Okay, ladies and gentlemen, we are now going to be learning about how to have exponents with common bases and how we would multiply and divide those bad boys. Okay, so our rules for zero and negative exponents still apply. We can't have zero exponents in our answer. We can't have negative exponents in our answer, so we have to remember those skills. I put a little box here. Let's not forget about our zero negative exponent rules. And again, anything to the zero power um, really results to 1 because we're talking about dividing that same base ultimately. Um, and then here, if we have a negative exponent, we know that we have to move it from one side of the fraction to the other. Doesn't necessarily make it a negative value. So let's get right into it here. Basically, our rule is when we have a common base that we're multiplying, we would keep that base and add the exponents. Okay, so here's a couple examples. Here's obviously the rule, the theoretical rule that we have a common base of a that we're multiplying together. And then we simply take the number of m, whatever that exponent is, and the number of n, whatever that exponent is, and we add them together. And so here's a numeric answer, 4 to the third times 4 to the fifth. We basically keep that base. It's very tempting to want to multiply 4 times 4 gives us 16, but we don't do that in this case. The shortcut here is we keep the base, add those exponents. So we keep the base of 4, add the exponents 3 plus 5. We end up getting 4 to the 8. And also, if we have negative exponents for the b here, we have b 7 plus negative 4. Okay, we add those exponents and we end up getting b to the third. So the kind of rule as to why it works is if we have x to the fifth times x to the second power, and you can kind of see here, if we're multiplying using x, you could see how this could kind of look like another x to the 1. So we got to be careful here. So that's why I left this example here so you can kind of see how confusing it can get. Typically, we would want to use this big kind of like filled in circle here to represent multiplication. Okay, so I would recommend doing that as we move forward here. But you can see here, x to the fifth is really x times x times x times x times x. Okay, and all these have little tiny ones of exponents there, times the x squared, which is x times x. So the easy way to go about doing this is we would keep that base, x, and we would add those exponents, 5 plus 2. So we have 5 here plus 2 here gives us a total of 7. So when we're multiplying this particular expression here, we have x as a factor 7 times. Okay, we're multiplying it 7 times itself. So that's really interesting. So when we're really talking about multiplying powers with the same base, we want to add those exponents. Let's not get confused. We would multiply coefficients, and you'll see some examples of that soon, but we want to add those exponents. So looking at this example here, we have 8 to the third times 8 to the sixth. Really what that is talking about is saying 8, if we were to simplify this, we keep the base of 8, and we would add those exponents. So I would throw a 6 in here, and of course 3 plus 6 gives us 8 to the ninth. And I did this quick calculation up here. 8 to the ninth also gives us 134,217,728. So I would also accept this numeric answer. Ladies and gentlemen, if you have a numeric problem here, don't hesitate to use your calculators, okay? It's all good. Here's another one. So our base here now is in parentheses, so we need to keep that base in parentheses. We have 0.5 raised to the negative third times 0.5 raised to the negative 8. Okay, so we are basically adding the negative 3 plus negative 8, and that would give us 0.5 to the negative 11. But I know what you're thinking. We can't leave that answer like that. So we have that negative exponent. We know we got to throw it downstairs when we're talking about the fraction. So we have 0.5 in the denominator raised to the 11th power now. So that becomes a positive exponent. And if you wanted to really know what that really stood for, 0.5 raised to the negative 11th, which is the same thing as 1 over 0.5 raised to the 11th, gives us 2048. So I would accept either answer, the numeric answer 2048, or I would accept 1 over the quantity 0.5 raised to the 11th. Here we have our common base of 9. So basically we can add all these exponents here. We have negative 3 plus 2 plus 6. And once we add those three numbers together, we would end up getting 9. Notice that we're not multiplying 9 times 9 times 9. We keep the base. All right, so make sure you're keeping the base there. When we add these exponents together, we end up getting 5. Negative 3 plus 2 plus 6 gives us positive 5. And of course, if you used your calculator, you could calculate that answer. So let's go through a couple more examples here. These are the rules that govern what we're able to do. So I'll let you pause this and you can just kind of read through these. I'm not going to go over this one specifically, but basically the important part of this is that we can group the big numbers together, the coefficients together, and then group the like exponents and the like bases together when we're kind of trying to compute this particular work. So our rule again is keep the base, add the exponents. So you can kind of see in this example here, we have 4 times 9, which is, these are the coefficients that we need to multiply together. And then we have the common base of z that we're multiplying together. So our quick shortcut is we can add those exponents, 5 plus negative 12. Well, 5 plus negative 12 gives us a negative exponent, z to the negative 7. We can't keep that in our numerator, so we have to throw it downstairs. But of course, we have 4 times 9 gives us 36, and that stays upstairs. Again, if I was to expand this out, we would have 5 z's on the top, 12 z's on the bottom, and there we have it. That would, 5 of these would cancel out. 1, 2, 3, 4, 5, and so what we're left with then are 7 z's down in the basement, if you will. This one right here, we can multiply those common bases. That gives us, we can multiply the coefficients, the 2 times 9 times 3. Notice that they're all different numbers, so we can actually multiply them together to get 54. And then we take our common base. We have an a to the first, okay? We have a to the second. All together in the top, we have a to the third. And then we also have this b to the fourth that comes along for the ride. So this would be our simplified answer here. For letter C, you could throw this right into your calculator, or we can use our theory. We would keep the base 6, add those exponents, 3 plus 5 gives us 8. And that becomes a huge, beautiful number if you're talking about money. All right, letter D, we would keep the base in parentheses, and we add those exponents. Negative 4 plus negative 2 gives us negative 2. All right. Oh boy, I made a little mistake here. So we have negative 4 times 0.3 to the negative 2. So we're actually adding these two together. That gives us 0.3 raised to the negative 6th, and we would have to move that downstairs. So don't look at this here. I apologize. I made a mistake. Shame on me. What I did is I applied the division rule, which we're going to get to momentarily. So negative 4 plus negative 2, that gives us negative 6. And of course, we can't have negative 6 as an exponent in our answer, so we have to throw that downstairs. 1 over the quantity 0.3 raised to the 6th. Finally, here we have negative 4 times negative 1. Be careful of these negatives here. Negative 4 times negative 1 gives us positive 4. And then for the common base of x, we can add those exponents. I got to do the y separate. 1 plus 7 gives us x to the 8th. And then we also have this y to the 3rd that comes along for the ride. Okay, a couple more examples here. We have negative 1 times 1 gives us negative 1. So I have that negative out there. And we're multiplying 4 y's to 3 more y's. Altogether, we have 7 y's. And that would be our answer there. Here we have 6 times 3 gives us 18. So we could deal with the big numbers first, the coefficients that we're multiplying together. And then look at all these x's that we have multiplied through together. We have 8 plus 2. I'm just adding these exponents here, and then plus this 1 out here. Don't forget it. Even though it's not shown there, we can write a 1 there if there's no exponent written there. So we add these 3 together. 8 plus 2 is 10, plus 1 is 11, and then we end up with our answer, 18x to the 11th. For here, we have negative 4 times 7 times 2. Okay, so we can multiply those together. If you used your calculator, you end up getting negative 56. The way I was able to get that really quick is I did negative 4 times 2 gives us negative 8. Negative 8 times 7 is negative 56. Let's look at our C's. It's always good to go in alphabetical order. We have 3 plus negative 2. So we have 3 plus negative 2. Throw that in there. And then for my D, I have this D squared. So let's look at the C first. Once we simplify that, we have 3 plus negative 2 gives us C to the 1. We add those together, and of course we have the D squared that comes along for the ride, and that would be our final simplified answer. Notice that we cannot combine unlike bases and deal with those exponents the same. They're different. We have to keep them different. We have a coefficient of 12 here in this particular problem, so we got to bring that up front. We have j squared, and then we have a j to the first here, so we're going to add 1 here. And then for the k to the negative 2. Well, when we go to simplify this, you can kind of see that we can't have negative exponents in our answer, so we know that we're going to have to bring the k down. So what we're left with is 12. 2 plus 1 gives us j to the third. That's good and happy. It's positive, so he's going to stay up top. And then the k to the 2 is going to come downstairs. And once we move it downstairs, it no longer has that negative or ticket to ride. So it's positive down in the bottom. And then finally here, we have negative 2 times 3.5. That gives us negative 7. And then we have a to the third plus, actually, we're adding 3 plus negative 3. And of course, what we're going to end up getting is a to the 0. And of course, when anything to the 0 power is 1. So our final answer is just going to be negative 7 in this particular case. Okay, so there's all our answers when we're multiplying those common bases. We also have a quotient, a power to a power. A quotient of a power. That means what when we're dividing a common base, the shortcut here is we can simply subtract those exponents. So when we multiply, we add the exponents. When we divide those common powers, we want to subtract those exponents. And let me show you why. So if we have 5 to the fourth on the top divided by 5 to the third, what we really end up having here is we have 5 times 5 times 5 times 5 on the top, and we have 5 times 5 times 5 on the bottom. Well, anything divided by itself cancels out, right? It becomes 1. And so what we're left with here is just 5 to the first, okay? Or just 5. That either or would be good. If I was to do the shortcut here, you could see that it would be simply 5. That's our common base, so we keep the base just like we did with multiplying, and we subtract these exponents, 4 minus 3. And that gives us 5 to the 1. Okay, so there's 2 different ways you can go about doing it. You can expand it out, or you can do the shortcut method. Okay, so the shortcut method here for this guy would be we keep the base and we subtract these exponents. So we do 6 minus 9. All right, now if we expand it out, you can kind of see that 6 of these 5s will cancel out. And then what we're left with is there's 3 more on the bottom. So whenever we have a 3 on the bottom, or we have a negative exponent, in this case, we would have to make sure that we're bringing that power and base, or that power, downstairs. Okay, so 5 to the negative third ends up being 1 over 5 to the third. And of course, you can kind of see it in expanded form that we end up having 3 more 5s down in the basement there. For this guy, okay, the shortcut here would be x to the sixth minus minus negative 9. So, we have to subtract these 2 exponents here. Of course, what happens is if we were to bring this up top here, we have the 6 here, we have the 9 here. Altogether, we have 15 up top. And of course, 6 minus negative 9 is also 15. So that would be our simplified answer here. Did a couple extra for you just as examples. If we have common our different bases, we have to deal with them separately. So when we have 1a up top, we have 7 a's on the bottom. One of those will cancel out. That leaves us with 6 more a's on the bottom. And then once we bring the 2 b's up top, because we can't have negative exponents in our answer, we end up having 3 b's up top, and now the 2 more b's, okay, that ended up coming up. So altogether we have 5 b's. Or the shortcut is 1 minus 7 for the a's gives us a to the negative sixth, and 3 minus negative 2 actually gives us b to the fifth. And again, we can't have negative exponents in our answer. So you either want to do this kind of thing or this kind of thing, one or the other. It's your choice, whatever is easier for you. X to the fifth and x to the third, you can see 3 of them cancel out, leaves us with 2 x's up top. We have 6 x's on the top, 1 on the bottom. So one of those cancel out, leaves us with 5 on the top. If you wanted to throw this whole answer over 1, that would be totally cool too. Again, the shortcut is 5 minus 3 gives us x to the second. 6 minus 1 gives us y to the fifth. All positive, so we don't have to move anything to the bottom. Here we have 3 4s on the top, 2 on the bottom, so there's only 1 left. And then here for the x's, we could do the old switcheroo. We could bring the 3 x's up top and the 5 x's on the bottom. We end up having a surplus of 2 on the bottom, so we have to represent that. And these y's will end up canceling out. Anything divided by itself is 1. And again, the shortcut is common base of 4. 3 minus 2 gives us 1. And then -5 minus -3 actually gives us x to the -2, so that's why we had to throw it down in the bottom down there. So no matter which way you go about doing it, this would be our final answer. Last particular examples here. For these particular guys with fraction exponents, we just have to apply our rules. 3 to the 5th, or 3/5, I'm sorry, minus 1/5, okay, ends up giving us x to the 2/5. Okay, these are kind of radicals. We're not going to get too much into this, but fractions kind of deal with the same kind of rule as do whole numbers when we have whole number fractions or whole number exponents. Here, this is actually the theory involved, so we keep our base, and then we subtract our exponents, a minus b. And that would be our final answer for that guy. And then our last guy here, we have two parts. We have the big number parts, which are a fraction that we can actually reduce. And then we have the x over x, which of course you can easily see will cancel right on out of there. So the only thing we really have to deal with here is 6 over 8, and we could divide each by 2 or throw that in our calculator. And once we divide each by 2, we end up getting 3 over 4. 3/4 is just going to be our final answer there. Okay, so please do me a favor and email me, make a comment in our Google Classroom, whatever you'd like to help me help you if you have any questions or concerns. Other than that, I'll hope to see you on our office hours. Have a great day.